In section 3.3, we discuss the topic of molarity, which is a property of a solution, and we learn how to do a series of standard calculations using the concept of molarity. But first we should define what we mean by a solution. A solution is an example of a homogeneous mixture. But there's one thing that's kind of interesting about it. In a solution, there's always one component that is present in a greater amount than all of the others, and that component is called the solvent. Any of the minor components are referred to as solutes. So in something like a cup of coffee, you probably can quickly realize that the solvent, the major component, is going to be water. And then there's a bunch of other things in there, depending on how you have your coffee, that are going to be solutes. Perhaps you can recognize that coffee has a distinct brown color. That's due to the presence of substances called tannins. You see the same thing in tea. And maybe you like your coffee sweet, so there might be some sugar or sucrose in there. And they would be examples of solutes. And of course, the solute that coffee is most famous for, caffeine, would be present as well. When the solvent of a solution is water, we describe the solution as being aqueous from the Latin aqua, meaning water. And aqueous solutions are especially important because nearly all of biochemistry takes place in aqueous solution. So even in the deepest, darkest ocean, where there's like no light, the pressure and temperatures are extreme, because there's water around, we'll find organisms down there called archaea that are able to exist under those conditions. And people have looked at rocks from Mars that they can see have been weathered by water, and when they look at these, they see evidence for what indicates was life. So this is not definitive, of course, but it's evidence that where there is water, where there has been water in the past, there has been life. So aqueous solutions are particularly interesting for folks who are interested in biochemistry. A pretty important characteristic of a solution is its concentration, which is simply the amount of solute for a given amount of solution. For example, 3% hydrogen peroxide, well, we've got 3% hydrogen peroxide for every 97% water, is commonly used as mouthwash and to clean wounds and just kind of, as a gargle just to freshen your breath almost. 35% hydrogen peroxide, 65% water is used in the manufacture of food, but it's also used to clean baths and pools and spas and things, and you certainly would not want to put this anywhere near your mouth or an open wound. It would hurt a great deal, and definitely if you were to swallow it, you'd probably get sick and start vomiting fairly quickly. So the solution is important. It's not only the identity of the solute and the solvent that characterizes a solution. Probably the most common way of expressing concentration in chemistry is in terms of molarity, which is simply the moles of solute for every liter of our solution. Normally, we'll give the molarity the symbol uppercase M, or sometimes moles over liters. Those things are equivalent, and people will flip between them without explaining why they're doing that. So just to recap, the molarity can be calculated by taking the moles of your solute and dividing it by the volume of your solution in liters. So the first type of calculation that you should be familiar with doing is calculating the molarity of a solution. And the important thing is that we need to make sure that our amount of solute is expressed in moles, and if it isn't, we have to convert it into moles, and that the volume of our solution is expressed in liters, and again, if it's not, we need to convert it into liters before we put the numbers into our equation. So this example here reads, what is the molarity of a solution formed when half a gram of sodium chloride, and then they give you the molar mass, 58.44 grams per mole, is dissolved in water to make half a liter of solution? So we can see that we have the volume of our solution in liters, so nothing to do there, but the amount of solute is given in grams. So we're going to have to turn our grams into moles. And so the easiest way of doing that is you take the mass in grams and you divide it by the molar mass of the substance. And we're given all of those numbers. We have half a gram of sodium chloride and 58.4 grams is the 58.44 grams per mole is the molar mass of sodium chloride. So putting those together, we get the number of moles of our solute sodium chloride. So now we're just going to go ahead and calculate the molarity. So we take our moles of sodium chloride, divide it by the volume of our solution, and I've rounded here to two significant figures because both of the numbers in the problem were given to two significant figures. But note I didn't round the answer of the intermediate calculation, and that's important. You don't want to round any intermediate calculations. You want to carry through as many digits as you can and then just round once at the end. So let's have a look at a few problems from the OpenStax book. So in problem 1 here, it's relatively straightforward because we're asked to calculate the molarity of a solution where the moles of solute is already given and the volume of the solution is given in liters. So we can just go ahead and calculate the molarity using the numbers that are provided without having to do any conversions. So we got 0.44 mole divided by 0.654 liters, and then we're going to round that to three significant figures because each of the numbers that were given had three significant figures. So let's see what we get. 0.444 divided by 0.654, and to three significant figures that ends up being 0.679 molar. Okay, now the second problem here is a little more complicated because we're going to need to calculate the number of moles of our solute because that's given in grams. However, the volume of the solution is given in liters. So remember what we're going to need to calculate the moles of something. It's the mass in grams over the molar mass. So we're going to need the molar mass of H3PO4. So there we've got H3PO4. So let's see what we've got here. Our moles is going to be our mass, which was 98.0 grams, divided by 3 times 1.008 for the hydrogens. And then we got 30.97 for the phosphorus, and then 4 times 16 for the oxygens. So put that into my calculator. 98 divided by 3 times 1.008 plus 30.97 plus 4 times 16. And 1.000, 4 zeros, and then a 6 moles. So almost exactly 1 mole. And now we're going to calculate the molarity, which is our moles, 1.0006, over our volume, which was 1 liter. So we have to 3 significant figures a 1 mole per liter solution. Okay, so there are our 2 answers. And OpenStax agrees with me. Okay. Now, something that we can do with the 2 formulas that we've been using so far is we can derive an expression to get the mass of solute that's required to prepare a solution. And this is very helpful, especially in the lab when we'd like to know how much we need to weigh out in order to prepare a given solution. So we said right at the beginning that molarity equals moles over volume. And we also said that moles is equal, we can reorganize this and you'll see that moles is equal to molarity times volume. Additionally, we've been using this formula quite a bit. The number of moles of a substance is equal to its mass in grams over its molar mass. So what I'm really saying is that this, which is equal to moles, is equal to this, which is also equal to moles. So that gives us our fourth expression on this page here. And now you can see that if I multiply both sides by the molar mass, I get this final equation, which is what we want. It says that the mass of solute required to prepare a solution is equal to the molarity of the solution times the volume times the molar mass. And I just want to point out one thing here, that the volume needs to be in liters. The molarity obviously has units of moles over liters, and the molar mass has units of grams over moles. And so you can see, as long as your volume is in liters, all of the units cancel out except for grams, which are units of mass, which is what we want. So you want to go ahead and memorize this formula and practice using it. So here's an example problem. It says, what mass of sodium chloride, and it gives the molar mass of sodium chloride as being 58.44 grams per mole, is required to prepare 100 milliliters of a 0.5 mole per liter solution. So something I want to draw your attention to is that the volume of the solution is given in milliliters, and the molarity has units of moles per liter. So we either have to turn our milliliters into liters or our liters into milliliters. But one way or the other, we have to have consistent volume units. And what I did in this case, just to illustrate a point, is that when we have a molarity like 0.5 moles for every 1 liter, we can always rewrite that as 0.5 moles for every 1,000 milliliters, because there are 1,000 milliliters in a liter. So let's look at the problem at hand. We're asked to calculate the mass of solute required to prepare the solution. We know that the formula tells us that this is given by the molarity times the volume times the molar mass. And what I've done here is express the molarity in moles per milliliter, and that's okay, that's valid. So according to the problem, we get 0.5 moles for every 1 liter, or 0.5 moles for every 1,000 milliliters. Now I did that so that then I can use my volume in milliliters, because that's what was given in the problem. So you can see that they're going to cancel out. And then finally we have to multiply by the molar mass, and you can see that that leads to the moles cancelling out, and the only unit that remains is grams. And when I put that into my calculator, I then rounded to 2 significant figures, because the molarity was given to 2 significant figures and the volume was given to 4. So there we go. So I kind of used this alternative form here for the molarity, and you're welcome to do that if you want to. So the third big type of calculation that we'll need to master is what's called a dilution calculation. So what happens in a dilution is we take a solution that has a particular concentration and we take a small part of it. So I've got 1 liter here and I'm going to take half of it. So I take half of my solution, and so now what I've got in that half that I've taken is half the number of moles that I originally had, and also half the volume. Then I'm going to dilute it by adding an equal volume of solvent. And so this is going to double the solvent volume, the solution volume. So we end up with a solution that is 1/2 what we started with. So that's a typical dilution, right? We take a small proportion of what we call a stock solution, and then we add some solvent to it to generate a more concentrated solution. Now, the key thing to recognize is that the number of moles that we take from our stock solution is always going to be equal to the number of moles that we end up with in our dilute solution. And we know that moles is given by molarity times volume. So the number of moles taken from the stock is going to be the molarity times by the volume of the stock. And notice here I've used C to indicate concentration. And then the number of moles that ends up in the dilute is going to be the concentration of the dilute times by the volume of the dilute. So that's what we call the dilution formula. Most people write it like this: C1V1 equals C2V2. C1 is what you start with. I'm going to take V1 of that, and then C2 and V2 are what we end with. So I'll show you how we use it. You'll see that in this formula that there are 4 variables. Typically you'll know 3 of them and 1 will be missing. So it says, how would I prepare 25 milliliters of 0.1 mole per liter solution? So that's what we want to end with. So C2 is 0.1 and V2 is 25 milliliters. How are we going to get this? By diluting 2.5 moles per liter of a stock solution. So that is the concentration that I'm starting with, C1, 2.5 moles per liter. So the only thing we're missing is how much of the stock solution do I need to take? So I'm going to take the dilution formula and I'm going to reorganize so that I can solve for my missing variable. And there it is. So if I divide both sides by C1, I can solve for what I want. So to get the missing volume, I'm going to do C2 times V2 divide C1, and that gives me 0.001 litres. You can see how the unit's going to work. Now, I could have worked in milliliters and it would have been just fine as well. So how would I prepare this? I would take 0.001 litres of the stock solution and I would dilute it until I had obtained 25 milliliters. Here's another one. It says, how would I prepare 50 milliliters of a 1 mole per liter solution? So that's what we want to end up with. So C2 is 1 mole per liter and V2 is 50 milliliters or 0.05 liters. How we're going to prepare this is by diluting a 5 mole per liter solution. So that's what I'm starting with. So C1 is 5 moles per liter and V1 is what's missing. So I'm going to take the dilution formula and I'm going to divide both sides by C1 so that I can isolate V1, which is what I'm trying to solve for. And now I just got to do plug and chug and be careful not to confuse my numbers. C2 is 1 mole per liter. V2 is 0.05 liters. And C1 is 5 moles per liter. You can see that moles per liters cancels out, leaving me with the units of liters, which are units of volume, so that's good. So I have to take 0.01 liters and dilute it until I have 50 milliliters. So 0.01 liters is the same as 10 milliliters, so I would take 10 milliliters of the stock solution and dilute it until I had 50 milliliters. Okay, So that concludes section 3.3 on molarity. We began by defining what we meant by a solution. We then defined molarity and the formula for calculating molarity. We combined two equations and got an equation for the mass of solute that's required to prepare a solution. And then finally, we talked a little bit about dilutions and the dilution formula.